Hello, everyone. We'll be going over at a high level for this presentation, zero knowledge proofs. So first, let's go over some history. So the idea of zero knowledge was first conceptualized by these three professors who published a paper in 1985 titled The Knowledge Complexity of Interactive Proof Systems. So in their paper, they sought to answer one simple question, which was, how much knowledge should be communicated for proving a theorem? To do this, they developed a framework for measuring knowledge in bits. We won't get into the exact details of these measurements, but let's think about how this would relate to the idea of zero knowledge. So obviously, some information does need to be communicated, such as whether the information is true or false, which is one bit. But how much more information needs to be communicated than that? Let's suppose, for example, that Alice has solved a discrete logarithm problem and wants to prove to Bob that she has solved it. She could just give Bob the answer, and Bob can verify it, and that would show that Alice has solved it, but that's more information than Alice would like. Perhaps Alice could give Bob an algorithm, and Bob can run the algorithm to solve it. And then that would verify that Alice, who has the algorithm, has solved it. But once again, more information than just this single bit of true false for whether Alice has solved the discrete log or not. So if we assume for now that Alice does have a proof that proves to Bob that she has solved the problem, we have there's one more question we want to ask. For instance, does she want this proof to be, Alice want this proof to be public or private? So if it's private, then only Alice and Bob, between them, only they should know that Alice has solved the problem. Whereas if it's public, if this proof were to be leaked somehow, and anyone who views it, if it were meant to be public, would be able to know that Alice has solved it. So let's take a little bit of a step back and talk about interactive zero knowledge proofs. So in general, for interactive proofs, we have two entities, a prover and a verifier. So the prover wants to prove a statement, which in this picture is labeled X, to the verifier. And in the interaction, the verifier can challenge the prover to a trial, which the prover would then have to respond to. So the idea of this trial is that if the prover does possess the knowledge, then they are guaranteed to succeed. Whereas if not, they would only have a chance. So in repeated iterations, the chance that the prover would succeed all of them becomes negligibly small. In interactive proofs, there's two conditions that need to be met, which are that they must be complete and they must be sound. So if the proof is complete, then if the statement is true, an honest prover can convince the honest verifier that the statement is true. This should, I think this should make a lot of sense, just taking at face value. A prover can prove that it's true if it's true. So just for our second condition, that it is sound. If the statement is false, no prover can convince the honest verifier that this statement is true, except by a negligible probability. What this means is that if the statement is false, the verifier cannot be convinced that the false statement is true, no matter what the prover does. If the prover cheats, if they're honest or not, no matter what they do, the verifier cannot be convinced that the statement is true if it is false, except by a negligible probability. And finally, what makes an interactive proof zero knowledge is that, of course, that it presents as no knowledge other than if it's true or false. But formalized, we say that every verifier that is given only a statement, but not whether it is true or false, can produce a simulation that looks like an interactive proof between an honest prover and a verifier. So what this means is that the real proof between the real prover and a verifier is indistinguishable from any fake proof that any verifier can make if they had no access to the prover. So, but in the real world, there isn't always a possibility of interaction, like synchronous interaction, for two parties to be able to communicate at the same time. So for that, we have non-interactive zero-knowledge proofs. One way to do this is the Fiat-Shamir heuristic, which is CMA secure. And essentially what it does is it replaces the verifier with a random oracle. So the challenges are randomized and from the random oracle. And concerning the private public question we had earlier, it must be public for the Fiat-Shamir heuristic because anyone who views the proof will be able to determine that, well, Alice, the prover, has the knowledge because there is no verifier that could be, could be maybe they're dishonest. But otherwise, it can still be zero knowledge. It does not give any knowledge other than just the proof of the statement. Another method is the common reference string, which essentially means that there is a string that holds some setup information that both parties, the prover and any verifier, is assumed to have in it's assumed that they all know this information. It's in common. And under certain scenarios, you can do a zero knowledge proof without interaction. So some uses of zero knowledge proofs in the real world, non-interactive zero knowledge proofs include ZK snark or zero knowledge succinct non-interactive argument of knowledge, which was developed in 2012. This is actually used today in cryptocurrencies, for instance, for encrypting a blockchain, such as Zcash and Tron. And it's used to like show that the sender has funds, for instance, like how much money you have without making it public, the actual amount of money, but at least enough that you have enough to show that you have enough money. Another example of protocol is ZK Stark, which is introduced in 2018 and stands for Zero Knowledge Scalable Transparent Argument of Knowledge. So I guess compared to Snark, it has scalability for bigger data and is more secure, even quantum secure, but it's much harder to prove and much more expensive to implement. So because of that, it's also slower than Snarks in practice to use as encryption. If we look at some other potential real-world applications in the future, there's, for instance, voting or social security or data analytics. So for instance, in voting, we can use zero knowledge proofs to allow voters to prove that their vote has been cast correctly, but without revealing knowledge of their identity or their choice, who they voted for. And in identity management, such as Social Security, we can use zero knowledge proofs to manage your information and for authentication. So users can prove their identity without having to provide too much sensitive information of their personal identity. And as for data analytics, we can use zero knowledge proofs to perform like large analysis of data without compromising the privacy of individual data points. So data analysts may not need to may not need to access the raw data but can still obtain information from them. So those are only just a few of the potential real-world applications of zero-knowledge proofs. So now let's take a look at a example, high-level, more in-depth example of an interactive zero-knowledge proof.
Now we'll show a high-level example of various protocols and discuss whether they are zero-knowledge proofs. Suppose there's a closed hallway that loops around at the end back to itself. It'll look something like this. At one end of the loop, hidden from view of the entrance, there's a door. Now, this door requires a passcode to be passed, so if someone wanted to travel through the full hallway loop, they would require the passcode to the door. Now, suppose Alice wants to prove to Bob, let's make him pretty, that she has the passcode to the door because she wants to sell him the passcode. So one example of the proof could be that Alice simply tells Bob the passcode, and Bob could try the passcode himself on the door to open it. However, this proof clearly gives more information than Alice would like to give because she can't sell the passcode to Bob after she gives it to him for free. So perhaps Alice also wants to share as little knowledge as possible, only allowing Bob to be convinced that she knows the passcode with no additional knowledge. So let's try a different protocol. As a second attempt, consider the following protocol. Alice and Bob walk to the entrance of the loop, and Bob waits at the entrance. And while Alice walks down path number 1, she attempts to pass through path number 2. Let's label these path 1 and path 2. If Alice successfully exits from path 2, Bob knows that she must have passed through the door and knows the passcode to the door. Let's assume for now that the probability that Alice can cheat, perhaps by leaving the door open beforehand or breaking down the door or teleportation, is all negligible. Bob can easily inspect the door beforehand to discount some of these probabilities. So this proof is sound. However, in this second protocol, it is still reasonable to assume that Bob would be convinced that Alice knows the passcode and that Bob does not know the passcode. So this protocol gives Bob less knowledge than the first protocol. So that's a success. However, if Bob were to secretly record this entire interaction, he would have a video of the proof. And he would be able to convince other people that seeing Alice walk through the loop of the hallway, she must have knowledge of the passcode. So even though Alice can prove that she knows the passcode to Bob without telling him the passcode, it is not yet zero knowledge because it gives Bob the ability to prove to others that Alice has knowledge of the passcode. Let's try a different protocol. So for a third attempt, still assuming that it is negligible that Alice can cheat, suppose Alice goes ahead of Bob down one of the paths without Bob seeing beforehand. In this example, she goes through path number 1 first. Bob then goes to the entrance, and he calls out either path 1 or path 2. And Alice's task is to exit from what Bob calls out. So if Bob sees Alice exit through the correct path, she passes that trial. Bob can repeat any number of trials to be convinced that Alice knows the passcode. So in each individual trial, since if Alice does know the passcode, she has a 100% chance of correctly going down the right path. But if she didn't know the passcode, she would only be able to exit through the same path she entered. So there would only be a 50% chance of success for each trial. Similar to the coin flip interactive proof discussed earlier, the chance that Alice will win every trial is negligible. Notice that if Bob were to secretly record this entire interaction, like in the second protocol, he never records Alice walking down the loop. So to a third party, this might not convince them that Alice does know the passcode. They would only see Bob call out a path and Alice exit from it. They cannot assume that Bob is honest. It is possible that he could have coordinated beforehand with Alice the order to which he would call out the paths so that Alice could always appear from that path and win, even if she didn't know the passcode. So this proof does provide less knowledge than the second protocol, as Bob doesn't gain the ability to prove to others that Alice has knowledge of the passcode. This third protocol is zero knowledge, since Bob only obtains the knowledge that Alice knows the passcode and nothing else, not being able to convince others that Alice has this knowledge. Now, if we are to let's consider a different variant on this third protocol. If Bob were to flip a coin, that can be heads or tails. In this video, and record this video to decide which path he would call out at each trial. And let's assume that the third party believes that Bob is being honest, that this is a fair coin. Then this variant would be enough to prove that Alice does possess knowledge of the passcode. The third party can be convinced that there is a negligible chance that Alice always wins the coin flip in deciding which path to enter if she didn't have the passcode. So this protocol is indeed not zero knowledge.